Hello guys, you're welcome to my channel. Today I'm back fully and I really appreciate you guys for your text and concern about my health. Thank God I'm okay now. So we are resuming back to continue from where we stopped, and we are to be looking at Newton's laws of motion. Now when you talk about Newton's laws of motion, it shows that you've understand all aspects of motion before you want to look at the law that binds it. So we are able to cover the linear motion, the circular motion, and the simple harmonic motion. If you are yet to watch that, you can just check the description box below to get the links to those videos. So today I'll be talking about Newton's laws of motion in detail. Please pay maximum attention. Thank you. If you are yet to subscribe to this channel, don't forget to do that now. That will be a factor that will encourage me, and you guys are the one that can really assist me to get to 100,000 of subscribers. You have really assisted me to get to 1,000, but we can do better. Thank you guys. Now let's quickly look into that now. Newton's laws of motion. Sir Isaac Newton stated about 3 laws that guide what or bind motion. And what are those 3 laws? That's what we are here to explain this afternoon. Okay, so when you look at acceleration, for instance, the acceleration of a body, for a body to accelerate, it's either by 2 types of forces, that is pull and push. These are the 2 forces that causes what? That causes a body to accelerate. But I'm not really going to be talking about this today, but I will just talk about it briefly. But I just want you to understand this, because a body can never be in motion except it is acted upon by a force. Are you getting it now? So that force has to be a contact force in some cases. If it is a constant force, then it has to be what? Either push or pull. I get a pull or push rather. Okay. So at times pull is called what? The unlike force, and push is called the like force. Okay, so we are going to be talking about that probably when we are talking about force field. We get there soon. So let's come back to the class now. Newton's laws of motion. So Sir Isaac Newton stated 3 laws, and we're going to be considering the first one now. The first law of motion. So when you talk about the first law of motion, guys, what does the first law of motion state? Let me tell you something, or let me remind you of something. You are not to memorize everything, but you have to understand everything in physics, and that is what is going to guide you in answering virtually all questions in physics without stress, even if you don't know them before. That's it, yeah. Now, what does the first law state? The first law of motion states that all objects, any object, including yourself, in the universe, they will continue being in their state of rest or uniform motion on a straight line, except it is acted upon by an external force. Okay? That is, for every object in the universe, they tend to remain in their state of rest if there is no force acting on them. Or they tend to continue being in motion without stopping, except if a force acts on them. All of this simply means. Let's understand it clearly now. For the first part, that states that an object tends to remain in their state of rest except they are acted upon by an external force. Let's take for instance that I have a platform like this, and I have an object of mass 10 kg on it. Now for this body to be at rest, then the force that is acting on this system must be at equilibrium. So for the forces acting on this body to be at equilibrium, it means this body has to be what? At rest. If the forces acting on this system is not at equilibrium, then it says that this body will be in motion. Are we together now? Okay, now let's see something. Immediately you drop this body on this platform, the body is erecting its weight on this platform. What is the weight of this body? Weight is given as mass times gravity, and practically gravity is 9.8 meter per second square. Then the mass of this body is 10 kilogram like this. Hence the weight of the body is going to be 98 Newton. Okay, so if the weight of the body is 98 Newton, then it shows that this body erects a weight of 98 Newton, which is also a force. Now, how do I know that the force is acting downward? The weight of the body is defined as the gravitational earth pull on a body. So gravity will pull it down. The weight is always pulling downward. And that's why you see the force moving in this direction. Now, for this body to be at what? At rest, the normal reaction, there is a force called normal reaction between this object and this particular what? Surface. And that force is acting in opposite direction to the weight of the body, according to the third law of motion. For every action, the action is that you place this what? Object on this platform. And the reaction is that what? The normal force is going to push it upward. Now, if this body will be at equilibrium, then it shows that the normal reaction is equivalent to the weight, which is also what? 98 Newton. Are we together now? So, because what? The upward force is equivalent to the downward force, this body will remain at rest. Are we there now? Hence, the net force on this body is equal to 0. So, if the net force is not equal to 0, then it shows that this body will said to be in motion. Hence, the first part of the law will not be obeyed. But if the net force is 0, then the first part of the first law of motion is obeyed. Now, the second part. The second part of this law is not going to work. It's against our daily activity. How is it against our daily activity? How is it not working? Because what? We have what we call gravity. Because of the gravity, the first law will not hold. Not only gravity, because of the air resistance. Not only the air resistance alone, because of frictional force. So because of all these what? Characteristics that we have in the atmosphere, that we have here where we are, then the second part of the law will not hold. Because if I have a surface like this now, I believe we understand the first part of the law. If I have a surface like this, if this surface is rough like this, the surface is a rough surface, and I drop a body on this body will only roll for a while before it stops. And that shows that it doesn't continue motion, because the second part of the law is telling us that what? An object in motion will continually in motion, except it is acted upon by a force. Now, it is acted upon by a force, which is what? Frictional force, because we know that friction always opposes motion of an object. Are we together? So, as this body rolls, it cannot roll longer before it stops. Hence, that second part of the law is not obeyed. Now, how can the second part of the law can be obeyed? Now, the second part of the law can only be obeyed in a situation whereby there is absence of air resistance, because if you take away gravity, there will be presence of air. Air will also affect the motion of this object. If you take away air, there is presence of friction. Friction will also affect the motion of this object. Hence, by the time you take away friction, you take away air resistance, you take away gravity, then the second law can be obeyed. And where can we find that? We can find that what? In a reference frame that it is in itself inertial. Because when you look at this first law of motion, the first law of motion stated by Sir Isaac Newton is exactly, let me say exactly, as the law of inertia stated by Sir Galileo Galilei. Are we together now? So, the law of inertia stated by Galileo Galilei is exactly the same thing as the first law of motion. Hence, we always call the first law of motion the law of inertia. Are we together now? The law of what? Inertia. So, if they ask you what is another name for the first law of motion, it's also known as the law of what? Inertia. Are we together now? Now, this law cannot work in all reference frame. What I mean by reference frame? A situation whereby a body is accelerating itself, you cannot find the first law of motion being obeyed. Are we together? I'll be talking about that when I'm talking about what? Moment of inertia and the likes. So, but for this class, let's just restrict ourselves to this score. Are we together? So in space, Where there is absence of gravity, there's absence of air resistance and friction. You see that all objects, they continue moving in motion. The Earth will continue moving. The Jupiter will continue moving. All other planets will continue moving. Why? Because they have to obey the first law of motion. And that is why you are told, or possibly JAMB usually asks this question, that what happened if the gravitational force of attraction between the sun and the earth suddenly ceased, and the earth moved tangential to what? To the circular track. Because if I have something like this, and here is the sun that is not perfectly at the center of the universe, and I have earth here. So if the gravitational force of attraction between the sun and the earth suddenly ceased, are you getting it now? It will cause this body to move tangential to to this circular track. And you may be asked that which law explains that, and that is the first law of motion, which we refer to as the law of inertia. Do we understand this now? So the law of motion will fully be obeyed in in space. That is, the second part of the law will be obeyed in space. Do we understand that now? Okay, if that should be the case now, let us move on. Because even the first part of the law is not absolutely obeyed. Let me quickly put into that. No object in the universe is absolutely at rest. That is, if I drop this body here now, if I drop this body right here now, and the body stop like this, to you are seeing the body to be at rest, right? But it's not absolutely at rest. Because where we are here, like myself, I'm in my studio now, shooting this video now, absolutely, this particular place I am is an initial reference frame. And for every initial reference frame, I have my acceleration to be approximately 0.3 meter per second square. So it's absolutely insignificant, because it's about it's about 30 times, or 10 times smaller. Let me put it like that. It's about 10 times smaller than 10 times smaller than the acceleration due to gravity. Are we together now? Hence, the Earth is accelerating with this type of with this minimum centripetal acceleration. So if the Earth is rotating with this minimum centripetal acceleration, you and I are also rotating with this. But because this particular acceleration is absolutely small, we don't experience it, we don't see it to be significant. Hence, no object is absolutely at rest. Hence, the first law of motion is not is not absolutely obeyed with our day-to-day activity. Do we understand this now? But can we prove this law? That is another question. Can we prove the law? No, the law is not provable. But why do we believe it? Yes, we believe and agree with the law because the law is always satisfied in every reference frame that has to do with okay, let me put it like this. The law is always satisfied. That is, the law is always correct in every measurement within their within their uncertainty. You don't get what I'm saying? This law cannot be proved. Are you getting this now? If the law cannot be proved, then why do we agree that the law is correct? We agree that the law is correct because all of the measurements that we are taking, the law is always correct according to the uncertainty of that measurement. That is why we agree with it. Is that taken now? Now, this law is the three laws of motion, they are very, very important in mechanics. Just like we have the Schrodinger equation as well. Okay, we get that as we move. Okay, so let's move down to the second law now. That's that about the first law of motion. Now, we want to talk about the second law of motion now. The second law of motion. So, when you talk about the second law of motion, we are talking about the law of force or the law of acceleration. What does this law state? The law states that every body will accelerate in the direction of the applied force. That is, if I have a body standing here now, this body is set to accelerate in the direction of the applied force. So if I apply the force like this, the body is set to accelerate in this direction. Hence, okay, let me state it like this, like we usually state it when we're in secondary school. So the second law of motion states that the applied force is directly proportional to the change in moment, to the rate of change of momentum. Are we there now? That is, the law states that the applied force on an object is directly proportional to the rate of change in momentum of the body. Now, before I go on, what is momentum? Momentum is the product of mass and velocity of a body and is denoted with small letter p. So momentum of a body is denoted with small letter p and it is mass times velocity of a body. Now, if a body has what? The momentum of a body, let's get something clear here. The momentum of a body determines how difficult it will be to stop that body. Because when you say momentum, now I want to teach now. Yes, I want to teach now. Let me teach now. When you talk about momentum of a body is the same thing as saying the mass in motion. Momentum of a body is the same thing as saying what? The mass in motion. And that is what will determine how easy it will be to stop that body if that body is in motion. For instance, if I have a train and I have a car, and this train is moving with a velocity of 2 meters per second, and the car is also moving with a velocity of 2 meters per second. Mind you, their momentum cannot be the same thing. Why? Because the mass of the train is absolutely greater than the mass of the car. Are we together now? Now, let's take for instance that the mass of the train is 100 kilograms and the mass of the car is 10 kilograms. For instance, just an instance. Definitely they are more than that. So, this will give us what? 200 what? Newton second. So if this one gives us 200 Newton seconds to be its momentum, the momentum of this one is just what? 20 Newton second. Are you here now? So it means that the mass in motion of this body will be stopped. For you to stop this body, you only need what? You only need a force of 20 Newton to stop it what? Within a second. Are you getting this now? For you to stop this car, you need a force of 20 Newton. But for you to stop this train, you need a force of what? 200 Newton. But they are moving with the same velocity. Yes, but their momentum is actually different. And when you say momentum, you are talking about what? The mass in motion. So, for you to stop a bus, and that's why it is very difficult for you to stop a train than it is to stop a car. Are we together now? And that is why it is very easy for you to stop a car that is moving slowly than a car that is moving with a very high speed. Because when the momentum is very high, to stop it will be very, very what? High as well. Unlike when the momentum is very, very slow. They will get out now. So if that should be the case now, we can now talk about what? This law now. So when you say change in momentum, that simply means what? Final momentum minus what? Initial momentum divided by what? Time. So if this should be the case, we have that F is proportional to what? To M into V minus U all over T. And you will agree with me that A is equals to V minus U over T, isn't it? So if that should be the case, F now is proportional to what? To MA. So if I remove this proportionality sign, I need a constant K. So F is equals to KMA. Now, you will agree with me now that for this F now, that equal what? KMA to be actually correct, like what we usually use, that F is equals to mass times acceleration. Then we have to take assumption that K is equal to what? 1. If you take the assumption that K is 1, then F is equals to what? MA. And that is what the second law of motion states. And we have the unit of force to be kilogram meter per second square. Now this kilogram meter per second square is equivalent to Newton in honor of Sir Isaac Newton. Is that taken now? So Newton is a derived unit. We only use this to honor the person that propounded the law that we are able to use to measure what? The value of what? Force. Do we understand that now? Now let us get something clear now regarding what? F equal what? Mass times acceleration. So if I have that F is equals to mass times acceleration, what will happen if I double the mass of a body and I keep the acceleration constant? If I double the mass of a body and keep the acceleration constant, then I will have what? 2 times 1. It means the force will also have to be doubled. If I triple what? The mass, the force will also have to be triple if I keep acceleration to be constant. Are we together now? Likewise, if I keep my mass to be constant and I double what? The acceleration, the force will also be what? Will also be doubled. Hence, we have that force is proportional to mass and also proportional to what? Acceleration. But what will happen to acceleration if I keep the force constant? If I keep the force constant and I'm looking for my acceleration, if I increase what? The mass of the body, the acceleration of the body tends to do what? To reduce if the force is constant. Are we making sense now? Okay? If I increase what? Mass, acceleration tends to be what? Tend to reduce if the force is constant. Likewise, if I increase acceleration and I keep the force constant, it means the mass of the body has to do what? Reduce. Is that taken now? Okay? Can we go on now? Okay, that's about what? The second law. But before I move on, I would like to show us something. I have that F is equals to mv minus what? Mu all over t initially if k is equals to 1. Agree with me? If I multiply both sides of this equation by t, I'll have that ft is equals to what? Mv minus mu all over t times what? T. Hence, this and this would cancel. So I have that ft is equals to mv minus what? Mu. And mv minus mu is called what? The change in momentum. Are we there now? So this change in momentum, which is force times what? Force times time, is regarded as what we call impulse. So impulse is the change in what? The change in momentum. Do we understand this now? Okay, we are able to talk about the first law and the second law now. Now, can the second law be proved? No, it can't be proven. And I would like you to understand something in physics. When you take assumption in order to achieve your aim, my brother, my sister, watching me right now, it shows that that law cannot actually be proven. I get it now. But we are going to, the question now is, if the law cannot be proven, do we agree with the law? Yes, we agree with it. And why do we agree with it that it's correct? It's because what? Like the initial one that we talked about, for every measurement, the law is always what? Is always correct within the uncertainty of that measurement. That's the reason why we agree that yes, this law is actually correct. But absolutely, it's not provable. It's just like the Schrodinger equation as well. Okay? So that's why, that's about that. Okay? Okay? Now, another thing that I need to talk about here is that this particular law will only be obeyed if the body is moving with a velocity that is absolutely reduced to the speed of light. Remember, the speed of light is 3 times 10 raised to power 8 meter per second. If I have a body that has this kind of velocity, then the law of what? The second law of motion will no longer be obeyed, because this now is absolutely greater than what Newtonian mechanics can handle. Newtonian mechanics cannot handle this. Then we have to talk about the relativistic mechanics, and that is when we are talking about what? The theory of relativity. Is that taken? I will be making video on that as we move on. Is that taken? Okay, so let's move on to the third law of motion now. Okay, what was the third law of motion state? Everybody knows that because it's like the talk of the town. So the third law of motion. So when you talk about the third law of motion, absolutely, you and I both know the law. Action and reaction, they are equal but opposite, and this law is known as the law of reciprocal. So if I have a force FA to be what? Action. This is going to equals to negative what? FR, which is what? Reaction. Because for every action, there is always what? Reaction. And the action and reaction, they are equal, but they happens in the opposite direction. For instance, if I want to throw this marker now, if I should throw this marker forward like this, what will happen to me is that if the marker should move forward, it's going to experience the force that I used to accelerate it. And my body will also experience the same force that I used to accelerate the marker. But I might not what? Move with the same velocity as that of the marker. But the force will actually be the same thing. Now the question is, why am I not moving with the same velocity as that of the marker? I'm going to explain that as we move. Now if I throw this body forward, what will happen is that I'm going to move backward. The force that caused the body to move forward is called action, and the force that caused me to move backward is called reaction. You can see the body move forward, I move backward. Action and reaction, they are what? They are equal but opposite. Because they are opposite, that is why you find this one to be negative. This negative is telling you that this and this are equal in magnitude, but their direction is absolutely what? Opposite. Is that taken now? Now, back to the question I raised when I was explaining what this third law, that why is it that if I throw this body forward and the marker will accelerate very fast, why am I not what? Accelerating very fast as that of the marker? Thank you. The reason is because my mass compared to the mass of the marker is absolutely what? High. The mass of the marker is small, but my own mass is what? Is quite big. And I told you initially that when you keep what? When you keep force to be constant, because the force is about to be constant now. Let me say it's constant, because this and this are equal. So the force acting on the marker is the same force acting on me. Are we together? But my mass compared to the mass of the marker is absolutely what? High. And that's why I cannot accelerate at the same rate or in which the marker accelerates, even if we are being applied by the same what? The same force. Okay? That's that about the third law of motion. Now, if I may ask you now, if you really understand what the third law of motion simply what implies, can you just answer this question? Let's take for instance that here is a river. I have a pool here, okay? And here is outside the pool. And I want to throw a ball such that after throwing the ball, I'm going to fall inside the pool. Get me clear? I want to what? This is a pool, and this is what? Okay, let me say this is myself. And this is a pool here. It's not like I'm inside the pool. I'm in between the pool and what? Outside the pool. So actually, I'm in between the two. Now, my aim now is to throw a ball such that after throwing the ball, I'm going to fall inside the pool. And the question now is, in what direction can I throw the ball? Should I throw it here? Should I throw it here? Should I throw it inside the pool so that I can also fall inside the pool? Or I should throw it towards what? This object outside the pool. You can pause the video and give answer to this question. And when you're done, you continue to listen to the answer. Absolutely. For me, to fall inside the pool after throwing the ball, I have to throw what? The ball towards this object. Because by the time I throw the ball towards this object with an action force, I'm going to experience what? A reaction force that will fall me back into this one, into this pool. That is why we say action and reaction, they are equal but opposite. The same thing happens when you are swimming. You push the water backward and the water pushes you forward. You are putting what? That is what we call what? An action. That is an action when you push the water backward, and when the water pushes you forward, that is what? Reaction. Is that taken now? Do we understand this at all? It seems I'm too fast in this class. I'm very sorry. Let's manage me like that. I'm just coming back, so I'm just trying to. Oh, okay, let's take that as an excuse. Okay, guys. So now let's go now. So you will now observe something that the more you push the water backward, the more you move forward. But you're not moving at the same rate in which your hand is moving. Yes, because the mass of the water you are pushing backward is not as much as that of your own mass, and that is why you see that the rate at which you are pushing the water backward, you're not moving at that same fast rate, but in a way you're fast. Is that taken out? So that's what about what the first law, the second law, and the third law. Now, before I go on or call it a day in this class, let's quickly look at what we call collision. Okay, we have to look at what we call collision. Now, when you talk about collision, what is collision? When you have these two bodies that hit each other like this, well, we said the two bodies collide. Now, collision can now be in different ways. I'll only be talking about 3 of it now. We have about 4 to 5 type of collision, but I'll be talking about just 3. One, have what we call elastic collision. I have 2, hyperelastic collision. And I have the third one, which I'll be talking about here, to be inelastic collision. Okay, guys, let's back to class now. I will cool down here. Cool down. Elastic collision, hyperelastic collision, inelastic collision. How can we recognize them? We are told that in elastic collision, momentum is conserved and energy is also conserved, because the law of conservation of linear momentum states that the momentum before collision in a closed system, let me take it like that. In a closed system, the momentum before collision is equal to the momentum after collision. Are we together now? Literally simple. So when you talk about what linear momentum, the law of conservation of linear momentum states that what in a closed system, the momentum before collision is equivalent to momentum afterward collision. If that should be the case, for elastic collision, both momentum. For elastic collision, like I said, momentum is conserved and energy is also conserved. But when you talk about hyperelastic collision, for hyperelastic collision, how can you identify that? If you have a mod, I said for elastic collision, the two bodies, they will repel each other immediately they collide, just like 2 billiard ball or the collision of 2 atoms of gas. So when they collide, they do what? They repel. But when you talk about hyperelastic collision, by the time, for you to get it clear, if you have a mod and you throw a stone inside the mod, the stone will not stay at the surface of the mud, but it's going to dip itself inside the mud. That is an hyperelastic collision. Are you getting this now? The stone entered into the what? Into the mud. That is hyperelastic. Are we together now? Now, if you now talk about what? Inelastic collision. For inelastic collision, momentum is conserved, but energy is not conserved. Are you getting this now? Momentum is conserved, energy is not conserved. Likewise, that of hyperelastic. Momentum is conserved, but energy is not what? It's not conserved. And when you talk about this inelastic collision, for inelastic collision, when the two bodies collides, instead of them to repel or for one to enter into each another, what will happen is that they will stick together and they will start moving together. This can happen in 3 cases if you are dealing with calculation. Let's quickly look at those cases now. So for case 1, you have a situation whereby when you have a body of mass m1 that is moving in this direction with velocity v1, and you have another body of mass m2 and it's moving with a velocity of v2. This is before collision arrives. Are you getting this now? Before collision, the two bodies are moving separately in the same direction. After collision, the two bodies stick together because it is inelastic. Are we there now? After collision. After collision, the two bodies stick together and move with common velocity. Now the question here is now what will be the value for the common velocity in which they are moving with? If we know what the mass of the first body, we know the velocity in which it's moving with before the collision, and we know the second one also. Now, what will be the common velocity that you are going to move with in respect to their mass? It's very simple. According to the law of conservation of linear momentum, momentum before collision equal momentum after collision. Because they are facing the same direction and momentum is a vector quantity, then we are going to have that momentum before collision is going to be the momentum of this one plus the momentum of the other body. Are we together now? Because it's a vector quantity, and whenever two vectors faces the same direction, we add them together. It's now going to equals to momentum after collision, which is m1v plus what? m2v. Plus m2v2 equal m1v plus m2v. So v is common here. If I factorize it out, I will have m1v1 plus m2v2 equal v into what? m1 plus m2. So if I factorize out v, I will have what? m1v1 plus m2v2 all over m1 plus m2. Do we understand this now? So this will be the common velocity that they are going to move with. So if this should be the case, what will now be the lost energy? Because we said momentum is conserved, but energy is not conserved. For us to get the what? The lost energy. So for the lost energy, okay, now I have to clean the board. Okay, the lost energy is said to be the kinetic energy before collision minus the kinetic energy after collision. Are we together now? So if that should be the case, lost energy is equal to 1 over 2 m1 v1 square plus 1 over 2 m2 v2 square minus 1 over 2 v square into m1 plus m2. And this will be the lost energy for the case 1. Now, case 2. For case 2, we have a situation whereby the two bodies, they are moving in an opposite direction to each other. So this is before collision. So after collision, they both stick together and move with common velocity as shown in the diagram. So this is after collision. So the same thing applies since momentum is conserved but energy is not conserved. So m1 v1, but because they are facing opposite direction, it's going to be negative. m2 v2 equal m1 v plus m2 v. So v now is equal to m1 v1 minus m2 v2 all over m1 plus m2. So this will be the common velocity for case 2. Let me put the absolute value so that in case if this one is greater than this, are you getting it now? You'll be able to subtract this from this. Are you getting it now? And if this one is greater than this, then you take the difference like this. So, but in order to place it, just put what? Absolute value so that you know that you are dealing with the positive sign. Is that taken now? Okay, correct. So if that should be the case, what will be the lost energy? Because there must be what? A lost energy. Yes. The lost energy is still going to be the kinetic energy before collision minus the kinetic energy after collision. Do you understand it now? Now, we'd like you to understand something here that it's not going to be what? 1 over 2 mv square minus no. Why? Because what? Kinetic energy. Energy is a scalar quantity. Irrespective of their direction, you are said to do what? To add them together. Is that taken now? So it takes to what? The same procedure like what we did initially. So the last case now. And that is case 3. If I have m1 moving with velocity v1, okay, let me call this velocity u because of what will happen here. And I have a stationary body m2. The velocity is 0. So that is when a body collides with a stationary body, and after collision, they both move with the same velocity. Hence, what I'm going to have here is that what? m1u plus m2v equal what? m1v plus m2v. So this will become m1u, because v is equals to 0, then this one will become 0. So I'll then have what? V into what? m1 plus m2. So v now is m1u all over what? m1 plus what? m2. And this is case 3 now, whereby you have what? A stationary body, whereby a body in motion collides with a stationary body, rather. So that's it about that. So momentum, the lost energy here is just going to be the kinetic energy before collision as usual minus the kinetic energy after collision. So it's as simple as that. So that's all about that. So in our next class, by His grace, we are going to be looking at questions on this particular topic. Have a nice day, guys. If you are yet to subscribe to this channel, don't forget to subscribe. If there's something I'm yet to cover or that I failed to explain in this class, you can let me know in the comment section. Then I will definitely respond to that. Have a nice day, guys. Thank you.